So in chapter 10 we were dealing with stoichiometry, and the most common problem is a limiting reagent excess reagent type problem. But for some reactions we want just the right amount. That is, if we have reactant A and reactant B, we want not to waste any of it. We just want to use just the right amount of B to react with A and just the right amount of A to react with B. Well, when we do that kind of thing in lab, we typically call that a titration. A titration will just get the right amount to react. And so we need some way of detecting when we hit the right amount. You know, the right amount could be done by weighing. So you weigh just the right amount of A and just the right amount of B, and that should react 1-to-1 without any excess or limiting. But sometimes that's not so easy to do in practice, especially if there's like impurities or other things that could be influencing a particular experiment. And so a titration is a fairly easy way of getting the right amount. And in a titration, we use typically we use something to meter or titrate, the amount of B in. So let's say we put some A in a container. Typically, if it's a solution, we use an Erlenmeyer flask rather than a beaker. And then what we'll do is we'll meter in some B here, and we'll just get the right amount of B. Now, the right amount of B is going to be what's called the equivalence point. It's the equivalence point is the correct quantity of B that we need. But sometimes we can't tell. I mean, there's nothing that tells us when we hit the equivalence point. And so we need some sort of indication that we've hit the equivalence point. And some of these aren't so easy to do. For our particular case, we have one that's fairly easy to use, and that's with this dye. This is the dye that we had up last week. It's phenolphthalein, and this dye is sensitive to acids and bases. So in acidic solution, that is lower pHs, we'll talk about pH later, but at lower pHs this is colorless. In basic solutions this turns pink or colored. And so what we need to do is we need to hit it right at the transition when it goes from colorless to colored. That's what we call the end point. And the end point and the equivalence point are very close in this particular reaction. They aren't exactly the same, but they're close enough that the error is quite small. And so what we're going to do is we're going to use a dye to tell us when we hit the right amount. And when we hit the right amount, the color changes. All right, so for this particular experiment, we're going to be reacting a base with an acid. So let's take a look at part 1, titration of an unknown base. The base is not unknown. We know what the base is. The base is sodium hydroxide. And what you're going to do is you're going to bring this flask, which is your 250 milliliter Florence flask, which is the round one. And so we have 2 flasks in there. You know what this one is called, the cone one? Erlenmeyer. This is the Florence flask. So bring a clean, dry Florence flask. It has to be dry, it can't be wet. Because what's unknown with this is the composition of this. That is, how much sodium hydroxide do we have and how much water? And so if it's wet, then you're adding more water, you're changing the composition, you're making it more dilute. And so what we want to know is we want to know the concentration, that is how concentrated is the sodium hydroxide in this. And so that's the unknown. We know what the base is. The base is sodium hydroxide. The unknown is a titration of an unknown concentration of sodium hydroxide with a standard acid. Now, standard, there's a government agency called the NIST, National Institute of Standards and Technology. Have you heard of that? I think they changed their name, but their budget is billions of dollars. And what they do is they make standards and standardization procedures. And so what is a standard? A standard is something that we know the composition of to a high degree of accuracy. And so what we want to know is we want to know the composition of our acid solution to a high degree of precision and accuracy. The accuracy is usually tested, but the precision is usually at least 4 sig figs. And so our standard acid, we know what the standard acid is. And our standard acid, in a liter of our standard acid, we have, let's see, is this going to work for me? Yeah. So in 1 liter of standard acid, we're going to have 0.1096. 0.1096 moles of pure HCl dissolved in a liter of this acid. And so we call it a liter of solution. And so if I take a liter of that standard acid, then I know to a pretty good degree of accuracy and precision that I'm going to have 0.1096 moles of HCl contained in that. HCl is normally a gas, and we can dissolve it in water. It's highly soluble. So that's a standard. And then what we're going to do is we're going to use this standard acid to figure out how much base we have in there. But I think today we're not going to worry about the stoichiometry. We're going to worry about the technique of titration. And you have to get good at titrations and in chemistry, because titrations are a common technique that we use. And so the objectives here, one, to be proficient in the techniques of titration. The way we do this titration is not the normal way titrations are done. The normal way titrations are done they're assuming you have a higher skill level. So the higher skill level means we don't have to set up as much equipment. But here we're assuming you have, you're a beginner. And if you're a beginner, then you make mistakes. And in Chem 1A, if you make a mistake, you throw it away and you start over. In Chem 4, if we make a mistake, what we're going to do is we're going to reverse the mistake and then retry. And if we keep making the mistake, we can just reverse one step or a couple of steps and retry. In Chem 1A, you have to toss it, you have to start all over. It takes a lot of time to do that. And so, but in Chem 4, we have more setup time. In Chem 1A, we have less setup time. And so what are we doing in this? Okay, well, we're going to learn the techniques of titration. Not a normal titration, but a beginner setup titration. 2, to gain familiarity with the concept of stoichiometry, we're trying to get what we call stoichiometric amounts. We want a stoichiometric amount of acid to react with a stoichiometric amount of base. What is stoichiometry? It's the right amount. That's what we determine in stoichiometry, how much quantities. To determine the molarity of a basic solution by titration with a standardized acid solution. So what we're going to do is we're going to use the standard acid to figure out how much base is in there. To determine the concentration, molarity is moles per liter. It's one of the common units of concentration or composition of solutions. Composition of solutions is usually given in molarity. How many moles of each component do you have dissolved in a liter of that mixture? And percentage by mass. Percentage by mass is also another common unit to express the composition of mixtures. Okay. Of acetic acid in an unknown. So this is part 2. All right, discussion. A standard solution is a solution whose concentration is accurately known, usually to 4 or more sig figs. So a lot of people, standard solutions and standards are very common in science. So if you don't know what a standard is, or standard solution, then that's something you need to know if you continue in science. If you don't, it's not so critical, but standard is pretty important. So even in Chem 1A, there's students who don't know what a standard is, which is surprising. But hopefully by Chem 1B, they know what a standard is. But it's surprising a Chem 1A student doesn't know. But at Chem 4, obviously you aren't going to know it. A titration is a precise analytical technique for determining the concentration. We use titrations for a lot of things. We could determine the concentration of a solution. This is one of the most common things that are done with a titration, but there are other things. And the way we determine the concentration of a solution is by adding stoichiometric amounts. So the procedure involves adding a standard solution to a solution of unknown concentration until equivalent amounts. Equivalent amounts would be stoichiometric. What is equal? Equal stoichiometrically equivalent amounts of each solution have been combined. In other words, titration is a method for determining the amount of a standard solution required to completely react with a given amount of solution of an unknown concentration. So we want to add just the right amount. We don't want to go over. If we go over, then we screwed up the titration. Obviously, we don't want to go under either. We just want to hit the right amount. What's the right amount? Well, hopefully we'll have what's called an indicator to tell us what the right amount is. So, in an acid-base titration, we wish to determine the point at which just enough base is added to completely neutralize the given amount of acid. This is the titration equivalence point. Okay, the equivalence point is just the right amount of base to neutralize the given amount of acid. So this reaction is just, I think, HCl with sodium hydroxide, I think, for part 1. For part 2, it's acetic acid. The endpoint is where an observable indication that we've hit that. And so when we look at this chemical reaction, we don't see any observable change. So the actual reaction for this is we have HCl and sodium hydroxide. This is part 1. And this is going to produce what? Yeah, good. NaCl and H2O. This is double replacement or acid-base reaction. And what's the driving force for this? What's the driving force for this reaction? There's no gas formation. So if there's gas formation, then that might give it an indication. Like, for example, if there's gas formation and we add the, let's say we add the sodium hydroxide or the HCl, then once we stop seeing bubbles form, then maybe that's the indication that we've hit the right amount. There's no precipitate. If there was a precipitate, precipitate's a solid. If there's a precipitate, then we could just keep adding until it stops forming precipitate. And then we'd know, okay, that's just the right amount.
Acid-base reaction.
Yeah, it's acid-base. So what's the driving force for acid-base reactions? Yeah, that's it. Coal acid. It doesn't have to be strong, but in this case it is strong. We're going from a strong acid, HCl, to a weak acid. In this case, the weak acid would be not sodium chloride. It would be water. Yeah. In this case, it would be water. So what we could do is we can just watch it and watch it until it stops forming water. But can you see the formation of water? I mean, these are what we call aqueous solutions. So there's lots of water around. What does HCl aqueous look like? It looks like a lot of water. Same thing with sodium hydroxide aqueous. This is the sodium hydroxide aqueous here. What does it look like? It looks like water. Here's the HCl aqueous. It looks like water, but it isn't. We call these CCSs. The CCS stands for what? Clear colorless solutions. What about salt water? Can you tell the difference? We're forming salt water. Can you see that visibly? No. We're not going to be able to see formation of a little bit of water because we already have tons of water in there. And the salt water is not going to give us a visual indication. We have no idea when we've added just the right amount. And so what we're going to do is we're going to put the hydrochloric acid in the flask here. And then we're going to add the sodium hydroxide to it and stop when we've hit the right amount, but we can't tell when we hit the right amount because there's no visual indication. And so what we're going to do is we're going to put our hydrochloric acid in the flask with the dye. You don't want to use too much dye. We only want to use a drop, maybe 2 drops of dye. And so let's continue reading. Where were we here? This titration endpoint is made observable by use of an indicator. The indicator is the dye. Now, the way we're going to use the indicator is we're going to put the acid with the indicator. It's going to be colorless. And then we're going to add the base. Initially, the base is going to neutralize the acid to form salt and water. But eventually, all the acid will be consumed. When all the acid is consumed and we add another drop of base, then that base is not going to react with anything. And so at the point when we have 1 drop of excess base, do you know what's going to happen to the color? The color is going to change because now we have some unreacted excess reagent. That unreacted excess reagent is going to color this, what color? Pink. And so what we're going to do is we're going to just keep adding base until we got too much base, and when we got too much base, the color changes, and then we got to stop there. Does that make sense? Okay, so I'm telling you this for it's easy to overshoot this because what we want to do is do we want to add a large amount of excess base to this? No. We want to hit this stoichiometrically. And so the hard thing is this. The hard thing is getting just the right amount of base without adding too much. And that's where people screw up. They add too much base. When you add too much base in Chem 1A, you have to throw it away, start over again. It's a big headache, and the students hate it, but unfortunately they have to do it. If we add too much base in Chem 4, do you know what we're going to do? We're going to reverse it by adding a little bit more acid. And so we're going to reverse the color change, and we go back to colorless. And then we try it again to add the base. When we try it again to add the base, what we want to do is we want to get it within 1/2 a drop. And so in other words, what we want to do is we want to go from colorless here to colored in 1/2 a drop of base. How do you do it in 1/2 a drop? Well, this is how you do it. What you do is you watch this, and then what we're going to do is we're going to add 1/2 a drop. How do you add 1/2 a drop? How you add 1/2 a drop is what you do is you suspend a partial drop on the tip. A full drop will fall down, but less than a full drop will hang on the tip. And so how do you get that 1/2 a drop to fall down? How you get that 1/2 a drop to fall down is that 1/2 drop that you're hanging on the tip, here you wash in with water. And so that's how you get a 1/2 a drop in there. And so hopefully what happens is this. You're colorless, and then you suspend a 1/2 a drop, and you wash that in, and then you're colored. That's not easy to do. But that's what you're going to try to do. So, so in Chem 4, things are more strict. Also, you have to watch out, is Chem 4, Chem 1A, Chem 4 is a lot less strict. Chem 4, we can do this reverse thing. Chem 1A, you can't. Also, watch out because sometimes in Chem 1A, they'll give like safety information at the beginning of the lab. And if they give safety information at the beginning of the lab, they might lock the door after they give it because they don't want to repeat the safety information. I don't usually do that, but there are a lot of instructors here that will do that. You know, after they give the safety information at the beginning of the lab, they lock it and tell you to come back to the next lab when they do the safety thing. And so just be aware of that. Chem 1A is going to be more strict. Well, Chem 4 too, depends on which instructor you have for Chem 4. I know stuff happens. So. Okay, for an acid-base indicator is a substance which changes color as acid or base. Another thing is, okay, in Chem 4 I don't mind reading this, but in Chem 1A you're going to have to read this yourself. A lot of people, I don't know why, but they don't read. And when you don't read, it gets very confusing. Even if you read, it can be confusing. So even if you read this and you're confused, then you want to ask questions at the beginning of Chem 1A or Chem 1B. So an acid-base indicator is a substance which changes color as acid or base concentration changes. For this experiment, convenient indicator is phenolphthalein. It is colorless in acidic solutions and pink in basic solutions. And so this is how we're going to use this to determine it. Pieces of glassware called burettes are used to precisely meter out volumes of solutions. These are burettes. And these burettes have pretty high precision and good accuracy. Usually for the accuracy we calibrate them to make sure they're reading correctly. But normally they're calibrated from the factory. Since they're calibrated and quite precise, they're quite expensive. Do you know how much this burette costs? No. More. No. This burette costs $200 pre-inflation. Now it's probably $400, who knows. But don't break it, because they will charge you. And people have broken these. I think I average maybe one broken burette every couple of years. You know, and the old prices are here. This is from 2018, 2019. Burette was $183.50, and students have broken these and had to pay that. It gets expensive. When I took organic lab, I broke lots of glassware. I think my bill at the end of organic lab was like $200 or something. And that was organic flasks and equipment are really expensive. They have special joints on them called ground glass joints, you know, so you can connect it like Lego pieces and stuff like that. And it gets expensive. So, but that was probably an unusually high bill. You know, most people break a lot less equipment. Test tubes are not a big deal. You know, test tubes are still fairly cheap, and so you probably don't have to worry about those. But burettes, yes. The other thing that's very expensive in this lab are these. These are really expensive. The graduated cylinders, surprisingly expensive. So these get lost all the time. Don't break. I've only seen a couple of breakages of this. I've seen lots of breakages of the burette. But mostly I've seen people lose these. And this is like $30. You don't want to lose it. All right, so we got the burettes. When a basic solution is added to a sample of acidic solution containing a drop, okay, this is what we talked about. You know, we want to hit the end point within a half a drop. Part one of this experiment is sodium hydroxide solution is titrated against a standard hydrochloric acid solution. So this is our reaction here. By experimentally determining the volume of sodium hydroxide required to neutralize. So what we're going to do is we're going to get two volumes. We're going to get the volume of acid and the volume of sodium hydroxide. And so what we're going to do is the burettes read from the top down. And so the top line here is 0. But you don't have to start on 0. In fact, people usually don't start on 0 because if you get it right on the 0, it takes extra time. What people usually do is they start below 0, but not too far below 0. They start a little bit below 0 and then just read the burette. That's a lot faster than trying to get the meniscus to line up right on the 0 line. And so let's first get a little refresher about reading the meniscus. Let me do that here. So when we fill it, we want to get V initial. And so this is going to be V initial for the acid or the base. And so we get V initial here. And then we're going to see a 0 milliliters here. And then 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7. Each of these are at 0.1 milliliter intervals. So if I'm taking a measurement, let's say this. Let's say the meniscus lies right about here. What we do is the water forms a concave meniscus like this. And what we do is we read right at the bottom of the valley. And so what I try to do is I try to get my eye level with the bottom of the meniscus here and then take the measurement here. And so usually what that means is, you know, it depends on how high this is sitting. If this is sitting this high, then it's kind of hard to read that. And so you could either lower it or you could take it off and just get it eye level and read it. Make sure you don't tilt it too much one way or the other. It should be vertical here. A lot of people, when they clamp this, they don't pay attention to how it clamps here. And even though this does look, does that look vertical to you? Yeah? No? It might look vertical to you because you're standing right here, but when I look at it, does it look very vertical? No, so just make sure it's vertical. That is, it's lined up here. You know, a few people always get it tilted. And so we could just carefully remove this. This is the burette, this is the burette clamp. Remove it from the burette clamp and read it. What is this reading here? What would you say this reading is? So this is, let's say, 0.1, that's 0.2, that's 0.3, 0.4, 0.5. What would you call that reading? It looks like it's between 0.1 and 0.2. So what would you call that? Remember, we're reading from the top down. So 0's at the top, and then 50 milliliters is at the bottom. You don't want to go past 50 milliliters because there are no more markings and you can't read it. And so we have to stop before 50. And so what is that reading there?
The very top is 0.
Yeah. This is 0. It's between 0.1 and 0.2. So what would you call it? Well, what's the number of your choice?
I would say 5. It's kind of a safe feeling. So.
Well, I wouldn't say 5 because it looks like it's not in the midway more. If it's midway between these two lines, then I would say 0.15.
It's not that big, that's right.
But it looks like it's closer to 0.2. Do you see that? And so I'd probably say 0.1, what?
0.17.
Yeah, 0.17, maybe 0.18. Would you agree? Yeah? No? So how do we get the initial reading? Well, first we have to clean the burette. And so when you clean the burette, let's see how much time. Usually we like to use soap and water, and we have something called a burette brush that allows you, it has a very long stem on it, and so it's just a cylindrical brush that you can brush all the way to the bottom of this. But we don't have any burette brushes, and what we're going to do is, hopefully this is clean enough. So all we're going to do is rinse this with tap water or rinse it with DI water. We're going to rinse it with DI water. Now, Sodium hydroxide is drain cleaner. We don't want to get drain cleaner in our eyes. And so you should wear goggles. Even though, I know a lot of people that are cleaning, but even when you're cleaning, splashes occur. And so if there's sodium hydroxide in here and it splashes into your eyes, it's going to burn. Have you ever gotten drain cleaner in your eyes? It's extremely painful. And it can cause severe damage. And so we don't want that. So what we're going to do is this. This is called a stopcock or a valve. When the valve is perpendicular, it's closed. When it's parallel, the handle is open. So this is the open position. This is the closed position. What we're going to do is we're going to use red for acid, blue for base. And so I'm going to prepare these by rinsing with DI water. When I rinse with DI water, I try to wash the inside walls of this here. And I'll get, some water in there and then just tilt this horizontally and then just rinse off the entire inside walls of this, like this. And then open the stopcock and then drain the water out the bottom. So I'll rinse it out like 2 or 3 times, and you can drain it out the top too. That should be adequate. Okay, once I rinse this with water, how am I going to dry it? Is it possible? No, it's not possible to dry. And since it's not possible to dry, what I'm going to do is this. I don't want to change the composition. This is red. I don't want to change the composition of my standard acid. Because if I add more water to this, I'm going to dilute it. Dilution is going to change the concentration or the composition. I don't want that to happen because I'm going to have more water in here. And so what I'm going to do is the initial rinse is with DI water. The final rinse is with acid solution. So for the acid solution, I could use this mini funnel. If you use this mini funnel, what often helps is to put your finger here and put a little air gap there. That way it pours quickly. If you don't, then this little mini funnel fills up quite quickly and overflows, spills out. And so with a little air gap there, you're right. But this beaker has a spout. Since this beaker has a spout, I would probably forego the funnel and just use the spout on the beaker. Maybe. Well, maybe not. It's kind of hard to do without spilling. So I'm just going to hold this with a little air gap there and then just pour this in. But I'm not going to pour too much. I'm going to pour a little bit in here, and what I'm going to do is I'm going to try to wash out the water with acid solution. And so I'm going to rinse this, except I'm not going to dump the acid into the sink. Instead, what I'm going to do is I'm going to get a big beaker and call this the waste beaker. I don't want to walk all the way over there, especially with something as expensive as this. So what I'm going to do is I'm just going to dump it into the waste beaker, like this. Okay, I'm going to rinse out the tip. We call this the tip of the burette. And the walls. I don't have to rinse out the outside walls like this. So the first rinse is just rinsing out the water. I might do this like 2 rinses or so. Should be it. Good. Or maybe 1 rinse, depends on how wet it was. And then I'm going to fill it. So I'm going to put a little air gap here so it flows quickly. And so I can fill this up. I'm going to fill it above the 0 mark. I need to fill it, actually I'm going to fill it up a bit above the 0 mark. The reason I'm going to fill it up a bit above, and we got to keep track of which funnel's which. We don't want to use the acid funnel for the base and vice versa. And so I got to keep track of the funnel. Here. The reason is because can you see air bubbles in the tip here? What I need to do is I need to purge all the air and whatever is stuck in here out. And so that's why I need a little extra here. And so the first thing is I'm going to purge the air out. Now, some of these air bubbles are very stubborn. Like I have an air bubble here that when I try to purge it out, it doesn't go all the way down. The air bubble goes about down here and then pops back up. This air bubble is going to be very stubborn. It's like if you have a balloon. Have you ever put a balloon like in a swimming pool or a ball in a swimming pool and tried to push it underwater? It's going to pop right back up, right? And so what we're going to do is, if you try to push it deep underwater, it's going to get more and more difficult. But if you just try to move it horizontally, it's pretty easy. And so what we're going to do is I'm going to tilt this. Even though this is full, look how far I can tilt this. This thing is full, and I can tilt it almost horizontally, and it's not spilling out. And then what I'm going to do is I'm going to push the air bubble out horizontally, like this. And so I have my waste speaker here, and all I'm going to do is I'm going to open this and then gently shake it back and forth and watch the bubble escape out the tip. Actually, I'll just do it up here. There's not much. And so, okay, now the bubble's gone. Oh, no, there was still a couple of bubbles left in there. Okay, and you do this into the waste beaker here. But I just spilled a little bit of acid. It's all right. This acid is not terribly concentrated. It's only 0.1 roughly molar. And so it's not too bad. Okay, now it's below 0, but you know what? I'm not going to refill it. Refilling is a hassle. All I'm going to do is I'm going to read it. And so when I read this, I'm between 2 and 3, and it looks like I'm between 2.5 and 2.6, and it looks like I'm right on the 2.6 line. So if I'm right on the 2.6 line, what do I call that? 2.6. If it's right on the line, we call it 2.60. And so my initial volume is 2.60. That's fine. I'm not going to hassle with getting this right to 0. It's a waste of time, and it's considered poor technique. And so if you spend a lot of time trying to get to this to 0, it's bad technique. All right. That's the acid burette. HCl is not that hazardous, but sodium hydroxide is quite a bit more hazardous. And then we have the base burette here. And so what was the procedure for cleaning the base burette? Yeah, pretty much the same thing as acid. Initial rinse with? We don't have distilled water. Do you know why? Too expensive. What do we have? Deionized water, yeah.
You gotta stop making burettes and pay for distilled water.
What's that?
You gotta stop making burettes to pay for distilled water.
Yeah. Well, if you guys break enough burettes and we charge, let's say, we charge double the cost, then we can probably afford the distilled water. $400 for a burette. Would you pay that? I don't know what the cost is now. Maybe it is $400. Everything else is. Gone up significantly. All right, you don't want to waste this. You don't want to waste the base because, you know, people always run out of base. And when you run out of base, then going up to the stockroom, they're not going to be very happy. You know, have you ever seen that movie Oliver Twist? When he asks for more porridge? Yeah, you're going to get that kind of treatment. So don't ask for more base if you can help it. So be careful not to waste too much base. So when I do my final rinse with base, I'm going to be very careful. And so I'll do the rinse with the base. And then I'm going to dump it in the waste beaker.
For these solutions, is it alright if it's mixed or something?
Yeah. You'll notice when you get the acid, not so much. If it were more concentrated, if it was 6 molar, it'd start to burn, just like a heat burn or something. But the base is going to be very slippery. The base is very slippery because it's just breaking up your cells, basically. Cell membranes. So you don't want to use the base. Bases, soaps are usually very basic. So it's like soap. You get soap in your eyes, you've just gotten base in your eyes. But this is drain cleaner, so be careful with this. Remember, we have 2 funnels, one for the base. Don't get them mixed up, otherwise it's going to be all screwed up. All right, and then fill this. And then we prepared our acid burette and our base burette. All right, what we're going to do is we're going to measure out approximately how many milliliters of acid. And so let's continue with the instructions here. Obtain the HCl solution in a clean, dry, labeled 250 milliliter beaker. So bring a clean, dry, beakers are easy to dry. Just give it a rinse. 250 milliliter beaker to the stock room. They're going to put the acid in there. The base is going to go into a clean Florence flask. Labeled, this one's already labeled NaOH for the base here. These ones are more difficult to dry. Okay, so it gives us the rinse procedure. Rinse the acid twice with 5 milliliter portions of HCl. Allow some to run. I usually rinse it first with a water. Fill the burette. Repeat this procedure for the sodium hydroxide. Get rid of the air bubbles. Make sure there are no air bubbles. Okay, you need to drain it to a convenient starting point between 0 and 15 milliliters. Then record this. So we're going to record the initial volume to the nearest hundredth of a milliliter. So we need 2 decimal places. If you do this to 1 decimal place, then that's not a titration. I don't know why, but a lot of people, when they collect the data, they only get 1 decimal place. This has happened even in Chem 1A, and you know that the person has very poor technique. They don't know how to read the burette properly, and so don't be that person. Make sure you read this to the nearest hundredth. That is 2 spaces after the decimal. If I see this, then usually that's a lot of points off. Like 50% off or more. Depends on the circumstances, but I see this once in a while. All right, so we're going to run about 20 milliliters of acid. What we're going to do is we're going to put about 20 milliliters of acid into our Erlenmeyer, but we're not going to record it. You know why we're not going to record it? Because most likely you're going to make a lot of mistakes. And that's not going to be the final amount of acid. If this were Chem 1A, you'd record it, because that's the final amount. But since this is Chem 4, you're probably going to have to do a lot of back and forth. And then we don't want to, each time we go back and forth, we don't want to have to reread it. What we're going to do is once you hit it perfectly, that is, what is perfect? Yeah. When you titrate within a half a drop, good. When we hit it perfectly, then we're going to stop and record the final volume of the acid and the final volume of the base to how many decimal places? To 2 decimal places, and then we're done. So we're taking 4 measurements. Volume of the acid initial, volume of the base initial, volume of the acid at the very end, and the volume of the base at the very end. So initial amount of acid is going to be about 20, but don't worry about it. Just get about 20 in there, we're good. And then we're going to add a drop or 2 of phenolphthalein. If you add 1 drop, then always add 1 drop. If you add 2 drops, always add 2 drops. And so they say add about 2 drops. Well, just make sure you're consistent. You add the same number of drops to each time. So 1 drop is enough. But you could do 2 drops if you want. All right. Now, when we do this titration, this is what we do. The first titration, we have no idea how much base this is going to take to neutralize it. And so let me do a quick titration for you, just to show you what you're looking for. And so I have my base burette. I haven't filled it yet. So I've rinsed this already. I'm just going to fill this. Oops. Watch out. These are very small funnels and prone to overfill. But you got to use a funnel with a Florence flask. And so I'm going to get this above the 0 mark, and then I need to get rid of what in here? Air bubbles. So let's see. Usually I'll tilt this, and then, yeah, there it goes. So that was easy. That took only a milliliter. So I have, it's still over the 0, so I'm going to drain some more here. And then mark this. I have it right on the 0.2, so I'm going to call this 0.20. Okay, then I'm going to pour about 20 milliliters in here. So all I do is I'll just open this. Oops, that popped out. That was almost $200 or $400 worth of burette there. Lost. I think I could get the faculty discount free. So about 20 milliliters. That's good enough. And then I'm going to add a drop of phenolphthalein. Okay, then I'm going to mix it. When you mix it, you just swirl it. This is the nice thing about Erlenmeyer's. It's easy to mix by swirling versus a beaker. If you swirl a beaker, it's going to spill outside quite easily. And so Erlenmeyer, because of this, it's really easy to mix vigorously. All right, I have no idea how much base it's going to take. And so the first one's going to be a throwaway. I'm not even going to bother trying to get this to 1 drop. And so I'm just going to let it drain in here and then watch the color. See when the color turns pink. Do you see it? Is it turning pink? Yeah? Oh yeah. Do you see that pink color there? That's what you're looking for. But the thing is, if I swirl this, what you want to do is you want to make sure that pink color lasts for 30 seconds. The pink color has got to persist for 30 seconds, and it does. So am I done? No, I'm not done. Because do I know if that was within a half a drop? No, I have no idea if that was within a half a drop. You know, I just stopped when it turned pink like this. And so what I'm going to do is I'm going to reverse this. And so I'm going to reverse this slowly. I'm going to add 1 drop here and then see if it reverts back to colorless. Oops. I accidentally put in 4 drops. So I put in 4 drops there, and you know what? It's still pink. So I put in another 4 drops. Is it still going to be pink? It's still pink.
You want like what's it called? A light pink?
No.
Or tint?
No, I want it to go back to colorless.
So you just have to add more when it becomes colorless?
I added 3 drops there. And it's very faint. Do you see that very faint? It's still faintly pink. It's very faint. It's almost colorless, so I'm going to only add 1 drop now. So let's see if I can just add 1 drop here. by slowly rotating this. Yep. Oh, I got 2 drops there by accident. All right. Now, do you see it?
It's okay.
Actually, it's because of the color of this. Do you see any pink in there?
A little bit.
Yeah, maybe. I'll add 1 drop. I added 1 drop, but there's a half a drop hanging. If there's a half a drop hanging, I'm going to wash it in. Because the burette would have recorded that half drop, but that half drop didn't actually go in there. And so I'll wash it in. And then I'm trying to rinse off the side of this to catch any splatter that might have occurred. Okay, now is it pink? No. Okay, so now I'm going to go back here, and I'm not looking for a pink. I'm looking for it to go from colorless to pink within a half a drop. And so what I'm going to do is I'm going to suspend a half a drop. Actually, there's already a half a drop suspended on this. I'm going to wash that half drop in. So I wash that half drop in, and then see, did it turn pink? No. And you know what? I don't know how far off I am, so I'm going to add a full drop. Okay, I just added 1 drop, and I don't see any pink. Do you? You got to watch out because of the LEDs. LEDs are giving it a purple color on the surface. Okay, I'm going to add another 1 drop. Oh, shoot. I added 1 drop, but there's a half drop suspended. So that half drop suspended I'm going to wash in. And then I'm going to rinse off the side to make sure there's no splatter. Any pink? Actually, no. It's that light. When I go over here, actually, maybe, no, there is pink. Do you see pink? Yeah. Yeah, I see pink, but it has to last for 30 seconds. So I'm going to wait and see if this lasts for 30 seconds. If this lasts for 30 seconds, then I'm going to stop here. I'm going to look on this. You can get a white paper towel. That's probably the easiest. And then look. Since we went with the LED lights, it's harder to see. Harder to see the pink. But it didn't last for 30 seconds. And so what I'm going to do is I'm just going to suspend a half a drop on here. So I'm going to just open it, and then the drop is going to get bigger and bigger, but it's not going to fall. And then I'm going to stop and then add this. Okay, so it's a little pink. Let's just see if it lasts for 30 seconds. Okay, what happens if I overshoot? Let's say I'm trying to get a half a drop and all of a sudden 4 drops fall in. Then I got to go back and forth until I can hit it to within half a drop. All we're looking for is we're not looking for, it's going to be very faint, the pink color. But we aren't looking for a certain color or intensity. All we're looking for is it to go from colorless to colored within a half a drop, and it has to stay colored for 30 seconds. What a lot of people do is they go, oh, okay, I just want to get a light pink color. But a light pink color could mean you overshot it by a milliliter or 10 milliliters because it's going to stay light pink. So I just overshot this. I put in an additional 2 milliliters here. And you might go, oh, okay, that's good enough, but we're over to 2 milliliters overshot. Do you know how many drops 2 milliliters is? That's 40 drops. I overshot this by 40 drops. That's how it looks like. Some people, when you look at it, it's so dark that they probably overshot it by 10 milliliters. You know, if we overshoot this by 10 milliliters, the color is going to be a lot more intense. Uh-huh. They have things called spectrometers that can read the color of the solution that we could use, but we're just going to use our eyes. It's hard to see. It's hard to see And so there's another way we can tell if we're doing a good job or not. This is the other way we can tell. So we're going to do this. This is by back titrating, going backwards, forwards until we get it just right. The other way we're going to tell if we're doing a good job is number 11. Number 11 is this. We're going to calculate the molarity of NaOH for each solution. If the values do not agree within 0.5%, run the fourth titration. We're not going to do that yet. What we're going to do instead is we're going to do this. We're just going to, as an alternative to number 11, we're going to calculate the ratio. We're going to calculate the volume of sodium hydroxide over the volume of HCl. And so we're not going to do the stoichiometry calculation just yet. We just want a quick check. The quick check is this ratio should be the same on each titration. It should require, so if we use 20 milliliters, let's say we require 20 milliliters base, then it's the 1-to-1 ratio. If we use 30 milliliters, that should require 30 milliliters base. It should still be a 1-to-1 ratio. And so what we're going to do is we're going to calculate the ratio of base to acid or acid to base, it doesn't matter which one. And then those, each trial should agree within 0.5%. And so let's say I do this and I get certain ratios. So let's say the first one came out to 0.9953. The second one came out to 0.9861. And the third one came out to 1.0253. And so let's say this is trial 1, trial 2, trial 3. So I'm going to do 3 trials, and I need to make sure that these agree within 0.5%. So what I'm going to do is I'm going to pick the smallest one and the biggest one and use those and see if the smallest and the biggest one agree within 0.5%. And so what I'm going to do here is I'm going to take the small, well, let's go with the biggest. I'm going to take the biggest ratio minus the smallest ratio divided by the smallest times 100%, and this has to be less than 0.5%. If this is greater than 0.5%, then you need to do trial 4, and then pick the 3 best. You do a fourth one. All right, any questions? All right, for those of you who came in late, we got to worry about the sodium hydroxide hazard. Sodium hydroxide is drain cleaner. Don't get it in your eyes. If you get it on your hands, you'll feel slippery. If you get it on your hands and they feel slippery, do not rub your eyes. You know, a lot of people end up rubbing their eyes and they get drain cleaner in their eyes. Wash your hands. If your skin feels slippery, wash your hands. You know, we could use a little soap and water and wash it off. It doesn't burn. The HCl will burn a little bit, but at this concentration, it doesn't really burn. I think at higher concentrations, if you have like 6 molar or 10 molar, you'll get a chemical burn, and it'll start feeling uncomfortable. Even at this concentration, it feels uncomfortable. Did you just see that? A drop fell down here. That's a leaky burette. What we have is do you see the screw here on the end? We can, if your burette is leaking, tighten the screw, but don't get it so tight that you can't twist the knob. And so you want the knob to be easy to twist, but not too easy that it's leaking. And so if this is really loose, look at what happens. Do you see all the drips coming off this? That's way too loose. And so we need to tighten this up, but make sure you can still twist. All right, so you're going to work individually on this. Hopefully we have enough burettes, but everybody needs to get practice. Let me double check that we have that. I think we do have enough, so.